In exercise 1006, we're going to look at an application of the exponential equation or function, and an application of it, or an example in the real world, is there are some things that grow according to the exponential function, that if we wanted a formula to represent how something was growing, we would have an exponential formula, and there are some things that decay according to the exponential formula as well. Just a little bit of revision, because it's a little while since we've looked at exponential. From the previous exercise, you might remember that exponential means that the x is the exponent or the power. Or you might have it complicated a little bit by putting another number at the front, a to the x. The most critical thing is that x is the power. That's what makes it exponential. X is the power in the equation or the formula describing what's happening, describing the growth or describing the decay. So it says any quantity that increases according to an exponential function, and if you're having problems with function, just think equation. So if we've got an equation that describes how something is increasing, then we say that it's experiencing exponential growth. It increases slowly at first and then very rapidly. So some examples of where that happens are population growth. So a few people in the beginning, not multiplying very quickly, but once there are more people there and they're producing more children, then the population increases very rapidly. And another good example of exponential growth is a bushfire. So it starts off, nothing much is happening in the beginning, and it's not until a substantial amount has been burnt, and then we've got a huge fire front because it's burning a much bigger area now, or along a much bigger line, that the amount of bush that it then continues to burn is bigger again. So we say that, yeah, they're two examples in real terms of growth situations that if we had an equation to describe how it was growing or how it was increasing, then the equation would be exponential. The other defining feature is you'll only get exponential growth if a is a number greater than 1. So this number here in this position, this number, has to be a number bigger than 1. So here's the example. A bushfire is spreading through a forest. The amount of area burnt is modeled by the exponential function. Area is 5 times, so 5's like that b up here. Here's your 1.22, which tells us it's going to be a growth because the number in the a position is bigger than 1, to h. Now, h is your exponent. The number of hours is the thing that is varying also, and that's in the power position or the index position. A is in hectares and h would be time in hours. I think I'll pause the video and draw the graph. We know that basically an exponential graph did this sort of thing, so it's starting off going only increasing slowly at first and then much more rapidly. So we've got a bit of an idea of what our graph should look like. So you can see I've filled out my table of values. Where I would normally have x in the table, it's going to be h, because in the formula it's usually x that's in the power, but we've got h as that power. A is what we're measuring, and it's like the y value. So I've got my y values, and I found those just by using the formula. This 5 times 1.22 to the h. So you can see there that I've calculated them using the calculator, and actually the calculator was really worked really nicely because I could just do rewind, hit delete, and put in the number I required, and just make that up so I can see the equals. And you can see that to the power 4, well, I just wrote it as 11, but that's using the new calculator, and you can use it with that benefit. You don't have to type in the whole sum every time. I've then graphed I've set up my axes. So you'll notice that it did say age from 0 to 6, but I only used the 4 values, 0, 2, 4 and 6. And then used up as much of the horizontal axis as I could for 6 hours, and likewise the vertical axis, making sure I could get to at least 16.5. So I then went about plotting them, and it doesn't make a great curve, but it's sort of in the right shape that it should be. So then, so I've done A, which was to graph the function. What was the initial amount of area burnt? Initial means in the beginning, T is equal to 0. When T was 0, there were 5 hectares burnt. What area was burnt after 3.5? Well, here's 3.5, and what we strongly encourage you to do is to put your construction lines. That's not actually going to work. So here's 3.5. Let's take that across. It's so close to 10. We would say approximately 9.6 hectares. Estimate when 20 hectares. So I'm going to have to extend my graph up until I get to 20. So again, using construction, I'm going to go from 20 across till I hit the graph, and that's going to come down just before here, which is a bit over 6.5 hours. Again, approximately 6.5 hours. These are just approximate when we're reading from a graph. What are the limitations of this exponential? What does that mean? Well, limit means, is there a time when the equation actually doesn't apply? And the answer to that is yes, because normally we would draw our graph with an arrow on the end. I'm not going to draw the graph with an arrow because I'm not going to indicate that this bushfire goes on forever. Bushfires don't go on forever. They either burn out the entire amount of bush and thereafter they stop, or they get put out. So before they've entirely burnt the bush, the amount of bush. So the limitations of this exponential are time will be restricted. It means it won't go on forever because a bushfire will not burn forever. Or a bushfire will eventually be put out. Or will it just eventually stop? Okay, I think you'll be right to do exercise 10.06.